So today we will discuss measurement errors and how we can reduce them in our results. So essentially, we will be talking about a simple approach where we can not only characterize measurement errors in a given quantum computer, but we'll also study a method of reducing errors in our final results. So when we run a quantum algorithm, we know that quantum computers that we have right now, they are very noisy. And there are many sources of errors that make the computations deviate from the ideal expectation that we have. So for example, the results that we get from the simulator. And there are many ways, and to actually reduce all of those errors, we need fault tolerant quantum computers. And that's not what we are going to discuss in today's class. But there's one part of errors which relate to the final stage in the algorithm, which is the measurement errors. That's what we are going to talk about today. And we will see how we can reduce them in the final results. And of course, if your algorithm, has a lot of qubits and a lot of gates, which mean most of the errors in the final results would be coming from the algorithm itself, and very few because of measurements. So when we implement measurement error mitigation on these types of algorithms, which are, have a longer depth, and then they have many qubits, the effect would be minimal, but we will be able to see the effect. But if we implement measurement error mitigation on shallow algorithms like, Dietz-Jozsa, Bernstein-Vazirani, and few others, we'll see that this mitigation technique can improve the final results very much, and make the results, nearer to what we expect from a noise-free quantum computer. So let me start sharing my screen, and then we can discuss it further. Okay, so the main discussion today is mitigating measurement errors, but let's briefly discuss the sources of errors, and then we will discuss measurement errors and how to mitigate them and how to characterize them. So the errors actually creep up at several stages in an algorithm. The first point is, you can say, the errors in qubit initializations. So we usually, a lot of our algorithms start our qubits in cat 0 state. But when our quantum computer does implement them, there might be slight errors in the initial configuration. And then of course, errors come when we do unitary operations, including single qubit gates, for example, rotations, some X, Y, Z, etc. gates, are control NOT gates, and so on. So a lot of the time, the errors creep into the system when we do these unitaries. Number one, the unitaries are not perfect, and number two, during these unitary operations, the noise from other sources can also disturb our qubits. And even when we are doing something to some qubits, are not doing anything to others. For example, we are just doing identity operation, which means that we are not doing anything. Even then, the errors are coming in, in our system because of the noise that is present in the system. And for example, we can characterize these errors for like decoherence noise or decoherence errors, which is a term which is used because of uh, the change in phase of, the relative phase of different states. And there could be, decay of some of these states. For example, we have some excited states and some ground states, and even during the identity operation, an excited state can decay to a ground state. And there could be other bit flipping. For example, 0 can go to 1 as well. It's not just that the 1 will always go to 0. Because of the noise present in the system, the ground state can also jump to the excited state. So there can be a bit flip type of error as well. So the errors are coming into the quantum computer all the time, even if you're not doing anything at all. And then, of course, in the final step, there are errors at the measurement stage. So we can call them measurement errors. And for example, if the state is something like p naught square root 0 plus some phase and p1 square root 1, and we should be getting probability of measuring 0 as p0 and probability of measuring this one state as the square of this, which is p1. But because of the measurement errors, we may not get exactly these probabilities. If there is a bit flip happening, that 1 goes to 0 and 0 goes to 1, then these probabilities would be different. Or even if there's combination of bit flip and phase flip, that can also give rise to error. And there are other types of sorts of errors. For example, decoherence or decay. So all of those can be expressed in terms of bit flip and phase flip error, because we know that any unitary can be written as a combination of x, y, z, and identity. And this y can be expressed in terms of x and z. So and these types of errors, by the way, which happen because of these which can be represented by these x, y, z terms, they are sometimes called Pauli errors. So at the measurement stage, these errors can happen, that whatever the state is at present, our measurement may not give an accurate picture of the state vector. So let's see how we can first of all know or measure these errors in a quantum computer. Let's say we have some actual quantum computer, and we want to characterize the presence of errors in it. So it's actually very easy and straightforward. We can, instead of worrying about individual errors, we can characterize the total measurement error like this. For example, you can prepare your qubits in a given state, and then do a set of measurements and see what's the state. For example, I prepare them in this 0,0 state. Suppose I have a 2-qubit system, and I prepare them in this 0,0 state, and then I do measure. So when I measure, ideally, and suppose I measure 1,000 times. Okay, so ideally I should get 0,0 1,000 times, and I shouldn't get 0,1. It should be 0. My 1,0 should be 0, and my 1,1 should be 0 as well. This should be my ideal measurement. Or if I plot its histogram, 0,0 should be with probability 1, and 0,1 and 1,0 and 1,1 should be with 0 probability. However, because of different types of noise, this 0,0 state during measurement can be read differently. So in practice or in reality, or in today's noisy intermediate scale quantum computers, uh, what we get actually is this, that we, even if we have prepared state in 0 0 state, what we get, we might get 0 0, let's say 990 times, and 0 1 perhaps 4 times, and 1 0 perhaps 5 times, and 1 1 perhaps 1 times. Usually a state that is only 1 bit away from the actual state is more likely than a state which is which can be obtained by more error. For example, to go from 0 0 to 1 1, the state has to flip both 0 and 1, which is less likely than 0 1 and 1 0. So when we do measurement, this is what we also observe. So in reality, we get 0 0 with a smaller probability, let's say 0.99. We get 0 1 with some probability, 1 0 with some probability, and 1 1 with some probability. So this is what we get actually on a quantum computer, and this plot will look different on different quantum computer. So a noisier computer will have these at a higher level, and this as a lower level, and a better computer will have the 0 0 state with higher probability and other states with lower probability. Okay. All right. So it means that if I think in terms of matrices, this is what is happening. That my ideal, or my you can say noise-free probabilities should have been like this, that 0 0 state should have come with probability 1, and but what I actually get is this, that my noisy probabilities or noisy measurement gives me 0.9 and perhaps 0.05, 0. I don't know, 0.4, 0.01, something like this. So instead of giving us this, we get this. And it means that I can write it as a matrix form, something like this. So if I want to characterize a relationship between my actual measurement, and let me represent it with a bar, which is a vector, through some matrix M, which represents the measurement process, from my noise-free, or let's call them, ideal probabilities. There is some matrix, which takes us from ideal to noisy, and that's a matrix that we have to guess. But before that, let me, go a little bit ahead, and suppose instead of preparing my state as 0 0, I prepare, let's prepare your qubits in 0 1 state. It basically means that if you start from 0 0, you can perform an X gate on this qubit and nothing on this. So this corresponds to the 0 1 state. And then we do this measurement. So ideally, I should get this. So 0 probability of getting 0 0 state, and 1 probability of getting 0 1 state, and 0 probability of getting other state. And if I, let's say, make my measurement 1,000 times, I should get 0 0 with 0 probability 0 times, and 0 1 I should get 1,000 times, and 1 0 0 times, and 1 1 0 times. But in reality, what I get is this, that I get 0 1, let's say 980 times, and I get 0 0 as perhaps, let's say, 10 times, and 1 0 as perhaps 2 times, and 1 1 as so 2 plus 10 12 and 80, so let's say 8 times. So what I my actual or noisy probabilities on a noisy computer, they are something like this: 0.98, sorry. So what I'm getting is 0 is with it's 10 times, so it's 0.01. 01 is 980 times, so this is with probability 0.98, and 10 is extremely less likely, 0.02, and 11 with 0.008. So this is what I'm actually getting. So if I start to put this thing and this thing together, so I can begin to get this element of this matrix M, something like this. So let's say I have a P noisy, and we can call it something A, B, C, D. And then there is this matrix M, and here is my P ideal. So you see, when P ideal was 1, 0, 0, 0, I was getting this result: 0.9, 0.05, 0.04, 0.01, which means that the first column of this matrix should be 0.0, 0.9, 0.05, 0.04, and 0.01. Because this transform this 1, 0, 0, 0 state to the state that we measure. Similarly, when my ideal state was this 0, 1, 0, 0, I'm getting this as output. So it means its second column should be 0.01, 0.98, 0.02, 0.008. So similarly, instead of preparing my system 1, 0, if 0, 1, if I prepare in 1, 0 state, I should measure 0, 0 with 0 probability, 0, 1 with 0 probability, 1, 0 with 100% probability, and 1, 1 with 0 probability, which means that my ideal probability distribution should be 0, 0, 1, 0. But in reality, what we measure is different from this. And suppose we measure, this state 0, 0 with the probability 0.2, and state 0, 1 with probability, I don't know, 0.04, and this state 1, 0 with some probability 0.91. So then this has to be 4, 2, 6, and 7, 0.03. Similarly, if I prepare my system in 1, 1 state and I measure all 4 states, then I can find this matrix as well. So let's say 0.01, 0.03, 0.04, and 0.92. So now this is my matrix M, which is essentially transforming my ideal states to what I'm measuring. So if I can, before I run my actual algorithm on a quantum computer, if I can somehow measure this M of that quantum computer, I will know what this quantum computer is going to do to my final state. Because whatever result in general come in, so now you see, for example, if I now instead of preparing this state, if I prepare this entangled state at the output, suppose I prepare this 0, 0 state 1 over square root 2, 0, 0, 1, 1, which means that my probability, ideal probability distribution should be half, 0, 0, half, right? Which is equal to half, 1, 0, 0, 1. So this is what I should get. if I do measurement, my histogram should be 0, 0 with probability half, 0, 1, nothing, 1, 0, nothing, and then 1, 1 with probability half. But I don't get this. I actually get this part and this part little bit as well, and they are also less than half. Can I predict even before measurement what I'm going to get? Yes, I can, because what my computer is doing, actually it's multiplying my ideal state with this matrix M, and that's what it is giving us at the output. For example, if I use this same matrix, this one, and suppose that our state here is half, 0, 0, half. Let's see what the measurement is predicting, what this matrix is predicting here. So I will get P noisy like this. So I'm going to get, so the first term is, this row times this column. So 0.9 into half plus 0.1 into 0, 0.02 into 0, and 0.01 into half. So I'm going to get 0.45 plus half of this. So half of this is 0.005. So 0.45 and 0.005 is 0.455. Let's now see what I'm going to get for this. So it's half of this, which is 0.025, and this into 0, this into 0, and half of this. So 0.025 and 0.015. It's 0.004, 0.04. Now let's see what do we get for this 0.0. So half of this is 0.02 and half of this is 0.02. So this is 0.04 again. And we can work out what we are going to get here. It's most likely something like 0.04565. Okay, now you see that we are getting some counts for 0, 1 and 1, 0, even though we should only be getting this. And this is coming from two sources. There are some, bit flips that are changing this state into, this, and this state. And there are some bit flips which are changing this state partially to this one, and this one. So that's why our measured probability is different from what it should be, even if our state, at the output is present with this ideal distribution. So this is what we are measuring. However, because of this characterization, now we have a hope that we can find the output without these measurement errors, partially, that we can, mitigate these measurement errors like this, because we now have this matrix M, which is converting our ideal measurement to noisy measurement. So all I have to do to recover my ideal measurement, all we have to do is invert the matrix. So P ideal should be M inverse dot P noise. So what you do know that you have a certain quantum algorithm to run, you run it, but then after you have found these noisy probabilities, you stop there, and then you go to the quantum computer again and you run another algorithm. If it is a 2-qubit algorithm that you run a 2-qubit noise characterization process, that you first run this circuit. So simply run this circuit, then and you measure it, and then you will have statistics for 0, 0, 0, 1, 1, 0, 1, 1. And then you run this circuit. Then you run this circuit. And then you run this circuit. So after you have ran these 4 circuits and measured them at the end, then you have been able to find all the 16 elements of this matrix M. Because for each circuit, you get these 4 numbers. Then for the next circuit, you get these 4 numbers and so on. So once you have run these, you have this matrix M, and now you have this matrix M. You can come back to your noisy results and multiply with the inverse of matrix M and get what you should be getting without measurement errors. Any questions so far?
Sir, when we are comparing our noisy with the ideal solution that we are getting, uh, how do we know that the ideal solution, what should be the ideal solution we should get? Are we like computing it mathematically, or are we running it on a simulation?
I'm sorry, I don't get your question. You are saying perhaps that when we get this ideal solution, we don't know, if this is what is present at the output or not. That's what you're trying to say, right?
No, sir. When we run the computation on a quantum computer, we'll always end up with the noisy initially,
Right.
and then we are converting it to the. We're saying that that this noisy is coming after it has been applied to a matrix that is adding the errors. But how do we know what the ideal state is supposed to be? I mean, there are multiple forms of errors.
Right. Okay. So this is a good question. And let me, give a summary of what we are doing, and I think that will clarify. So in general, this is what is happening. So if you have an algorithm, these are the steps. You have a bunch of qubits, then you run an algorithm, and then you get a certain state, and then you perform measurement on it. No, the errors are coming in this process as well. And actually, most of the errors are coming in this process when we are implementing different gates and we are going from one step to another step and so on. So by the time the state reaches here, it already has a lot of noise. And then measurement adds its own set of noise because measurement process is also noisy. Right now, what we are assuming, we are saying that we are not worrying about the errors that are happening during the evolution, during the algorithm implementation. For now, we are imagining that actually there are no errors. So suppose there are no errors that are happening, that are coming during the algorithm. So it means then whatever we are doing is now giving us a state over here. And then suppose the errors are only coming during the measurement process. So with this method that we have just discussed, we will be able to revert the impact of measurement errors and go to this state. No, I'm saying that you can imagine that there are no errors coming in, but the method that we have discussed, it's applicable in both phases. So in general, when we were getting output result here, it had errors from here and errors from here. So there you can say there is some measurement errors that are coming because of the algorithm, and there is some source of error which is coming from here. So the total error that you're getting, it's product of these two. So this is algorithm dependent. The errors that are coming in this part depend on algorithm, because if your algorithm has only few gates, the errors are few. If your algorithm has lot of gates, your error is going to be huge in this part. But this error is sort of independent of algorithm, only depends on number of qubits, because this is the step that is fixed. It only has these measurement devices at the end. So this part is independent of algorithm, and this part is dependent on algorithm. And what we are discussing is we are able to revert to whatever the state is here. If you want, you don't need to call it an ideal state. What you can call is the state just before measurement. So perhaps that's a better name. That with this process we will not be able to find the ideal probability that we found, but we will be able to find the probabilities that are just before measurement. So with this inversion we will be able to revert to the probabilities just before measurement. Does that clear?
Yes, sir. Thank you.
Okay, Ahmed, you also have your hand raised up. Please go ahead.
जी सर, I wanted to ask, जो IBM computers हम इस्तेमाल करते हैं, do they perform these corrections or not?
No. So if we want, we will have to do this correction ourselves.
So we would have to figure out the matrices ourselves as well.
They have provided subroutines that can do it, but we will have to apply this correction ourselves if we want to apply it.
Okay, thank you.
So far, the algorithm that we have been running on quantum computer ourselves, they didn't actually had any error correction in them. They were giving us the results from the raw results that are coming after working with the noisy gates and noisy measurement process. But from now on, we will be able to implement this slight noise correction on our algorithms, which depends on, which will be able to mitigate the measurement errors at least. So remember what I'm saying, that in general, you can say your error, they are coming up from, this measurement part and from this algorithmic part, whatever this, you can say your state is here. And by inverting with this thing, that if I multiply with this thing from both sides, we will be able to have errors in our results, which are only coming because of the algorithm and not because of the measurement process. So it's not a lot, but it's at least something. And you will actually, I'll show a couple of examples after this, where you will be able to see that if algorithm is simple, actually most of the errors are from measurement, and we will be able to get a much cleaner picture. But if algorithm is complicated, then most of the errors are from algorithms, and this mitigation will not help. But not help much, but it will still help a little bit. Asif, you have a question?
Ji, sir. Sir, let's suppose we do not have any algorithmic error. So
okay.
If we remove the measurement error by applying that matrix, can we get perfect results, like ideal results?
Yeah.
So, sir, what about the quantum uncertainty? The collapse is perfect. I mean, is there any uncertainty while when a state is collapsing?
Oh, no, but the uncertainty principle relates, two things. When we have, let's say, when we are trying to measure two properties simultaneously, that's when it comes in. But if we are working with, one type of property, we are just trying to find out if the, what's the state with respect to this observable, if the state is in this eigenenergy or the other eigenenergy, then we don't have to worry that. And even the small effect that would be coming from there, and actually it's related to the time that you take on the measurement. So essentially when we, measure if the state of the qubit is either 0 or 1, we are essentially measuring the energy of the qubit, right? Because let me draw this thing. So if we have this two-level system, so it's 0 or 1. So essentially there is certain energy here and certain energy here. So when we are studying if it is 0 or 1, we are essentially studying if it is collapsing to 1 or 0, which means that we are trying to measure the energy of the system. Now, the Heisenberg uncertainty principle relates energy and time. So, and their product, is has to be more than this h cut by 2 figure. And if we measure this for long enough, and usually this measurement time is several microseconds, and these energies are small, so we don't have to worry about the error that is coming because of this uncertainty principle, because that error is extremely small. And the beauty of this, measurement reduction is this, that all of those things are contained in this matrix M. So we will be able to revert that as well, because this M characterizes all the measurements errors. It might be coming from bit flip, from dephasing, from, from noise around, or even partly from this Heisenberg uncertainty principle, which is going to be pretty small. It's all contained in matrix M. And when we apply its inverse, we are actually reducing a lot of errors.
Okay, sir. Thank you.
Okay, perfect. So any other question? Abdullah Ahmed, you have a question? Your hand is raised.
जी सर, सर मेरा ये तय सवाल था छोटा सा कि जैसे आपने मेजरमेंट मैट्रिसेस अभी ऊपर बनाए, मेजरमेंट एरर के मैट्रिसेस आपने जिक्र किए कुछ, तो क्वांटम किसी भी एक क्वांटम कंप्यूटर का जिसका मेजरमेंट एरर का जो मैट्रिक्स होता है वो कांस्टेंट होता है फॉर एज इन अ सेट ऑफ मेजरमेंट्स हमेशा.
So good question. So actually, if we have, a very stable system, and statistically speaking, it's going to behave same over time, then what you are saying should be true, that we can just characterize this matrix M for one quantum computer once and for all. And then just, for each algorithm, we just apply its inverse, because we can save it somewhere in the memory, right? And that's how we should happen. But since, these quantum computers are also calibrated again and again, so after every few hours, these systems are calibrated. So these things, there are slight changes, not much, but the slight changes come and go. So that's why it's better to find this new matrix every time you run an algorithm. So hopefully in the far future, when these systems are stable and these calibrations doesn't have to be performed that often, then these things can be, hidden in the assembly part of the quantum computer, where when you run an algorithm, you don't have to worry about error correction yourself, and there is something hidden from you that's taking care of this error itself, that the results that you get, they're already error free. But right now, since these quantum computers are in experimental stage, and one idea from IBM, to put them in the cloud, is that different people work with them and maybe come up with different error correction strategies that are efficient and better than other people. And later on, when these systems mature, then these things will, become part of sort of the hardware or software. But right now, you have to do it again and again.
Okay, sir. Thank you.
Okay, so we are now going to do a couple of examples where, I will show you how to implement it in quantum algorithms. But before I, move forward, let me discuss one, trouble with the use of quantum computers and working with these, noise and error correction schemes. So we know that quantum computers are not available, for most of the time, at least not right away. For example, we submit a code and we forget, and maybe next year we get the results. At least for most of the good quantum computer, that's what the case is. Some, bunch of very noisy computers like Kyoto and Bellum and a couple of others, they are available in public domain, but and we can get results much quicker than the better computer. So what people have done then is instead of just running your algorithm on an actual quantum computer to see what's the effect of noise, they have provided this facility inside the software as well, that you run your code on a simulator. Actually, let's say you run it on COSP simulator, but you can mimic the effect of noise of a quantum computer by selecting different noise models. So you use noise models with simulator, and that mimics the effect of the actual quantum computer, but you are able to run your code right away. So you just press shift enter and your code is done, and the result is as if it has been, run on a quantum computer. And this is also a scheme that I will discuss today, that how to mimic a quantum computer with different noise models. But of course, I will also show how you can run these calibrations, these noise error correction using an actual quantum computer. So for that, we will have to work with the notebooks. So I'm going to end this session. And